Hello everybody, and welcome back to another geometry lesson. Today, lesson 2.6. That's right everybody, we have reached the end of Unit 2. Woo! And more good news, this lesson is a lot like sections 2.4 and 2.5. Again, we are working on our proofs. We've got 5 more theorems and postulates to show off today. First one is the right angles congruence theorem. All right angles are congruent. Yep, that's right. To the shock of nobody, every single right angle is the exact same angle as every other right angle. They're all 90 degrees. These two are congruent. Next up, we have the congruent supplements theorem. When we're looking at this theorem, I want us to consider 3 different angles. Let's draw them out. Let's say I've got an angle that looks like this. I've got an angle that looks like this. Hey, they almost look like they make a flat line. Interesting. Another set that looks like this. Hey, these ones also look like they make a flat line. I wonder if that's important. Let's call these angles 1, 2, and 3. Yes, indeed, this was intentional, everybody. I want us to take a look at angles 2 and 3. If combined, what would they make? Well, it seems like they would add up to make 180 degrees, or a flat line. Interesting. Let's look at angles 1 and 2. Same deal. They look like they would add up to make 180 degrees. The congruent supplements theorem basically says that if an angle is supplemental to another, and that angle is supplemental to a third, then the first angle and the third angle must be the exact same. They must be congruent. So the theorem goes, if angles 1 and 2 are supplementary, again that means add up to 180 degrees, and angles 3 and 2 are supplementary, then angle 1 must be congruent to angle 3. These two angles are the same. Very nice. Interestingly enough, this also works with complementary angles. Remember that complementary angles add together to make 90 degrees. So if we have two angles that look like they make a right angle if we were to push them together, and then another one here, where it looks like the big angle and this angle would make 90 degrees if we push them together. Turns out that this angle here, we'll call angle 4, and this angle here, we'll call angle 6, are congruent as well. It says, if 1 and 2 are complements, and I used the wrong numbers here. If 4 and 5 are complements, and 6 and 5 are complements, then angles 4 and 6 are congruent. That's right, 4 is congruent to 6. Love it. Next up, we have the linear pair postulate. This one is used very simply. The linear pair postulate happens when we have a, spoiler alert, linear pair. Recall that a linear pair happens when two adjacent angles form 180 degrees together. So the theorem goes that if two angles form a linear pair, They are supplementary. Two angles form a linear pair. They are supplementary. Last, but most certainly not least, the vertical angles congruence theorem. Remember that vertical angles are angles that are across from each other when two straight lines intersect. Here, we can very clearly see that 9 and 10 are vertical angles. We would say that 9 and 10 are congruent because vertical angles are congruent. Done and done. These 5 should absolutely go on your note card as reasons for your proofs. They don't show up as often as some other reasons do, but we should still be aware that they very well could. So, let's take a look at some proofs using this. The first proof we have down here, example 1, is use the given information to write a proof for the right angles congruence theorem. That's right, everybody. Remember that theorems must be proven before we can use them. I've already told you that all right angles are congruent. So if we look at the given 1 and 2 are right angles, we know from that theorem that 1 and 2 have to be congruent. I don't care about whether you know it or not. I want you to prove it to me. So, let's say angles 1 and 2 are right angles based on our given. Can you use the properties you know about right angles, maybe the definition of right angles, to show that 1 and 2 also have to be congruent? Pause the video and see if you can do it. Hopefully you've had a chance to try it out. If 1 and 2 are right angles, well, that means that the measure of angle 1 has to be 90 degrees. And if 2 is a right angle, then the measure of angle 2 has to be 90 degrees. That's just the definition of a right angle. Not too bad so far. What do we notice about this definition, though? We have two angles, and they both equal the same measure. So what can we say? Well, if two things are equal in a proof, we can set their other sides equal to each other. Since 90 and 90 match, we can say the measure of angle 1 equals the measure of angle 2 due to the substitution property of equality. Nice. Finally, the only thing we need to do is turn it into a congruence problem. It's an equal sign right now, so we know that to go from an equals to a congruence, we just have to use the definition of congruence. And that is a proof of the right angles congruence theorem. It's this proof here that lets us say if we have right angles, they must be congruent. Very nice. Let's flip to the next page and try some more. Before we do, I want to let you know something interesting. There are other types of proofs. We're not going to be learning them in this unit simply because we won't use them again, and I don't want to teach you something that you won't use again, but we should be aware that they exist. For instance, flowchart proofs are a common type of proof that uses boxes and arrows to show a logical argument, such as in example 2. Meanwhile, paragraph proofs don't have much organization at all. Paragraph proofs are just in paragraph form, which makes it for easy reading, not for easy proving. We won't be performing these proofs, but I do want you to be able to recognize them and understand them when we see them. So here we go. Example 2. We have to convert the flowchart proof that we see into a 2-column proof. So all I want us to do is to take the information from this flowchart and put it into our table. To do this, keep in mind that just like how a 2-column proof starts at statement 1, we need to start somewhere with the flowchart proof. And we have 2 starting places. Angles 1 and 2 are supplementary. And angles 3 and 2 are supplementary. Since they're both givens, I'm just going to write them in the same box with the word given as our reason. Can you try to fill in the other parts? See if you can. Pause the video and unpause it when you're ready. Hopefully you've had a chance to give it a shot, so let's see if we can do it together. We notice that these 2 boxes also use the same reason, the definition of supplementary angles. So why don't we also do that? Why don't we also put both of them into the same box? This is the definition of supplementary angles. Yeah, I'm really shortening these words now. Then both arrows connect up to this one. This means that somehow these 2 statements combined. According to the flowchart, it says that they combined using the transitive property of equality. The transitive property says that if the hypothesis of one statement and the conclusion of another match, you can match them. I disagree that the transitive property was used here. I think it's more just regular substitution, but hey, if it tells us that they use the transitive property, who am I to judge? Next up, we see that we use the subtraction property of equality to get measure of angle 1 equals the measure of angle 3. That's the subtraction prop of equality. Ending off with angle 1 being congruent to angle 3, because to swap from an equal sign to a congruent sign, we use the definition of congruency, or congruence or congruent angles. Done and done. Let's move on to the next one. We're at a good pace, let's keep it up. Fair warning for example 3, I goofed up on the printing here a little bit, and we actually need to add a 6th box. So if you could, please add a 6th box to this proof. Again, I'm going to give you a second to try it out on your own. If you're not trying these out on your own, you're not going to be able to understand them well, even when we talk about them. So pause the video and see if you can write a proof for this. All right. Hopefully you've had a chance to take a look. Let's see if we can proof it out. So our given is that TPS and QPR are vertical angles. This is our given. And somehow we need to prove that 49 equals x. It seems a bit off. Well, let's first off talk about what it means to be a vertical angle. Vertical angles are congruent. So that means that TPS is congruent to QPR. That's the definition. Sorry, that's not the definition of vertical angles. I am losing my mind. I'm sorry, y'all. That is the postulate that we just talked about. The vertical angles congruence theorem. I would probably accept definition of vertical angles too. Vertical angles congruence theorem. Next, we see that this is an equal sign, but we have a congruency symbol. So right out the gate, we should try our best to get rid of the congruency symbol, trade it out for this nice and shiny equal sign. The measure of angle TPS equals the measure of angle QPR. That's the definition of congruency. Now, from here, we sort of make a logical leap. We see that in the diagram, TPS is 148 degrees. QPR is 3x plus 1. I'm okay with you using that it's given in the diagram for this next statement, but what we're really doing is we're substituting TPS for what its measure is, 148 degrees. What we're really doing is substitution. So I'm going to substitute 148 for TPS, because that's what it measures, and I'm going to substitute 3x plus 1 in for QPR, since that's what it measures. I'm calling that the substitution property of equality. Part 5, we want to solve this. So the first thing we do is we can subtract 1 from both sides. That gives us 147 equals 3x. That's the subtraction property of equality. Then, to get x all by itself, we have to divide out that 3, giving us x equals 49. That is the division property of equality. Done. And very nicely done, if I do say so myself. Hopefully, as we've gotten more practice this throughout the unit, we've gotten a little bit better with understanding how to get from one spot to the next. All of this follows a flow. We just have to get in the rhythm to dance to the beat. Let's take a look at the final page here of Unit 2. We have 3 more proofs to do. So let's get to it. In example 4, we have to use this information to write a proof for the statement. Given that angle 1 is congruent to angle 4, well, that's an easy first statement. Given, we need to also prove that 2 is congruent to 3. So at some point in the proof, we're going to need 2 and 3 to appear. One thing we notice is that 1 and 2 are vertical angles, and vertical angles are always congruent. So would we be allowed to say angle 1 is congruent to angle 2? I sure think we can. In fact, we could also probably say that angle 3 is congruent to angle 4 for that exact same reason. They're congruent because they're vertical angles. This is the definition of vertical angles. We could also call it the vertical angle congruence theorem. Love it. Here, we see there are some things in common. Note the following. 1 is repeated twice in this problem, and so is 4. Interesting. I see these repeats as things that we eventually want to substitute. You can do all this in one step. I'm going to do it in 2, so it's a little easier to see. Right now, I'm substituting in angle 2 into this spot because they are equivalent. That is substitution property of angle congruence. Love it. From here, notice that this 4 here and this 4 here match, so we can substitute again. Angle 2 is congruent to angle 4. Once again, or sorry, not by angle 4, by angle 3. My bad. Angle 2 is congruent to angle 3 because we substituted in the angle 3 for that spot using the same reason. Substitution property of angle congruence. Done. Example 5 is compact, but is a little bit tougher. let's see what we're given. We're given that ABD and CBE are right angles. So we'll write that here. And that is our given. And we need to prove that ABC and DBE are congruent. Let me mark off these angles. ABD is a right angle, so I mark it here with that corner. And CBE is a right angle. I'll mark it off at this corner. What we're trying to prove is that ABC, this narrow angle in blue, is congruent to DBE, this narrow angle in purple. Well, to do that, we need to somehow first use the things that we are given. So I'm going to use the fact that these are right angles to show something else. We know that two angles that form 90 degrees are complementary. And since we really, really want ABC to appear somewhere in the problem, can we rewrite ABD to equal something that involves ABC? Well, if these are right angles, then according to the definition of complementary angles, we know that ABC plus CBD are complementary. We can say that A equal ABC and CBD are complementary. We can do the same thing with angles CBD and DBE. Angles CBD and DBE are complementary. That means we can use the definition of complementary angles once more. To finish off the proof, we know there's a theorem that involves two angles being complementary. I wonder which one that was. Here we have a theorem that says if two angles are complements, and then a third angle is the complement of the second one, then the first and the third one are congruent. And that's what we have here. ABC and CBD are complementary. CBD and DBE are complementary. That means that ABC and DBE must be the same. ABC has to be congruent to DBE by that theorem that we just mentioned, once again, the congruent complements theorem. There are absolutely other ways to prove this. You could have used your angle addition postulates and then flipped back and forth between equals and congruency. This is just a shorter way to do it using the postulate that we just learned. Last proof, this is supposed to be example 6, but it is written as example 5. There we go. I've filled in some of the information, but we need to use our given to once again write a proof. We're told that AB equals DE and BC equals CD. We have to prove that AC is congruent to CE. What a ride. Well, let's start off with our given. Our given is, well, given to us. AB equals DE and BC equals CD. That's our given. From here, all of a sudden, I gave you this. AB plus BC equals BC plus DE. Huh? How are we adding together like BC and DE? They're on opposite sides of the segment. Well, we have to look at what's going on here. The only difference between our first given and this is the addition of BDs. If that's the only difference, what did we really do? Aha! We must have used the substitution property of equality. Or not substitution, sorry, the addition property of equality. The addition property of equality lets us add the same thing to both sides. So of course we added BC on both sides. That's why they both appeared. Then we start substituting in something. Why would we substitute something? Well, as we are substituting these in, I want us to keep in mind the following. We still want to prove that AC is congruent to CE. Since AB plus BC we know will eventually equal AC, we should have the other side also equal our other segment, CE. So how do we make that happen? Well, CE is made up of CD and DE, so we replaced this BC here with CD. AB plus BC equals CD plus DE by the substitution property of equality. Love it. From here, we just mentioned that these segments are going to add together to make AC, and these are going to add to make CE. So why don't we just put those both down into the table? I'm going to write down that AB plus BC equals AC, and that CD plus DE equals CE. Again, that's just the segment addition postulate. Ooh, blanked out there for a second. Segment addition postulate says that. And lo and behold, we've got some more doubles. We see some doubles here, and we see some doubles here. So we can substitute them in. AC equals CE is what we get when we use the substitution property of equality. We're so close to the end, all we need is a congruency symbol. So to do that, we simply use the definition of congruence to turn that symbol around. And we are done. This proof was done in a bit of a weird way. I would have personally done it in a different order. I would have personally noticed that the segment addition postulate applies first, and then maybe I could have done some funky stuff with our given statements. That said, that concludes Unit 2 for us. Thank you so much, everybody, and have a fantastic rest of your night.